Black holes are among the most mysterious and terrifying objects in the cosmos. They are regions of space where gravity has grown so intense that nothing, not even light itself, can escape. For decades, scientists have tried to unlock their secrets, but black holes stubbornly defy our attempts to observe them directly. Instead, they lurk invisibly, shaping the universe through their immense gravitational pull. And yet, every once in a while, the universe offers us a clue, a chance to peek behind the cosmic curtain. One such moment arrived in January 2025, when the loudest gravitational wave signal ever recorded shook our detectors here on Earth and, in doing so, confirmed one of Stephen Hawking's boldest predictions from more than half a century ago. The story of this discovery begins long before 2025. In the early 20th century, Albert Einstein introduced his general theory of relativity, a radical reimagining of how gravity works. According to Einstein, massive objects curve the fabric of space-time itself, and this curvature tells other objects how to move. His equations suggested that, under the right conditions, a star could collapse into a singularity, an infinitely dense point surrounded by an invisible boundary known as the event horizon. The very idea seemed so extreme that even Einstein himself doubted whether such things could exist in reality. But as the decades passed, the evidence piled up, and black holes shifted from mathematical oddities to accepted astrophysical objects. Still, how do you study something that swallows all information? The answer came from another of Einstein's predictions: gravitational waves. When massive objects accelerate through space-time, they create ripples that spread outward at the speed of light, much like a stone disturbing the surface of a pond. Detecting these ripples is no easy task. They are unimaginably faint, but they carry with them the fingerprints of the events that created them. In 2015, humanity achieved a breakthrough when the LIGO observatories in the United States detected gravitational waves from two black holes colliding over 1 billion light-years away. That historic signal, known as GWW1FEM914, confirmed once and for all that black holes exist and that their violent mergers can be felt across the universe. A decade later, in January 2025, LIGO once again captured history. The signal, named GW250114, was stronger and clearer than anything observed before. Two titanic black holes had spiraled together in the darkness, colliding with such ferocity that the space-time fabric itself rang like a cosmic drum. For scientists, it was a golden opportunity. With a signal this powerful, they could test the very limits of Einstein's theory and probe one of the most famous ideas in black hole physics: Stephen Hawking's area law. In 1972, Hawking published a revolutionary paper showing that when two black holes merge, the total surface area of their event horizons must never decrease. In other words, the final black hole left behind after a collision must always have a horizon larger than the combined horizons of the original pair. This rule seemed counterintuitive, especially because black holes lose huge amounts of energy during mergers in the form of gravitational waves. But Hawking argued that the mathematics was clear. No matter how violent the collision, the area could only increase. The law was elegant, simple, and profound, but it had never been tested with the precision available today. The gravitational waves from GW250114 provided the perfect test. After two black holes merge, the remnant does not immediately settle into a calm, silent state. Instead, it undergoes what physicists call a ring-down, vibrating and radiating waves in a pattern that encodes its mass and spin. This process is remarkably similar to striking a bell. The tone and timbre of the bell reveal what it is made of and how it is shaped. Likewise, the tones of the gravitational waves carry hidden information about the black hole itself. By carefully analyzing the ring-down, researchers reconstructed the properties of the new black hole and compared its horizon area with those of its parents. The result? Hawking was right. The area law held firm. For physicists, This confirmation was more than a mathematical curiosity. It reinforced the idea that black holes, despite their terrifying complexity, are governed by simple, universal rules. They are not chaotic monsters, but rather elegant manifestations of Einstein's equations. The validation of the area law also strengthened confidence in general relativity itself, showing once again that this century-old theory continues to withstand every challenge thrown at it, even in the most extreme environments imaginable. And yet, the story does not end here. GW25014 was the clearest signal we have ever seen, but it will not be the last. As detectors grow more sensitive and more advanced observatories come online around the world, scientists expect to record hundreds, even thousands, of black hole mergers. Each one will provide new data, new puzzles, and perhaps new cracks in the armor of Einstein's mighty theory. If those cracks appear, they may finally lead us toward a deeper understanding of gravity, space-time, and the fundamental nature of reality itself. For now, though, we can celebrate a remarkable triumph. The cosmos has spoken, and it has confirmed that Stephen Hawking's vision of black holes was correct. Half a century after he proposed the area law, the universe itself has validated his insight. Black holes remain fierce and mysterious, but thanks to gravitational waves, they are no longer beyond our reach. Their secrets are beginning to unfold, and with each discovery, we step closer to unlocking the ultimate mysteries of the universe.